Good afternoon and welcome to today's machine design webinar titled Beyond Traditional Mold Making, Performance Gains and Conformal Cooling Advances with HP MetalJet M2 and INDO-MIM, sponsored by HP in partnership with INDO-MIM. I'm Sharon Spielman, Technical Editor of Machine Design with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties today during the session, please submit them into the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many as we can during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into that question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our speakers for today's discussion. Harish Sharinki has nearly a decade of experience in additive manufacturing research, applications, and business development. Currently, he serves as a senior applications engineer and strategic account manager at HP, where he has also held roles such as application engineer and technical segment lead for hydraulics. Prior to HP, Harish served as an application and manufacturing engineer at various companies focused on additive manufacturing. Jag Halla is the Senior Vice President of Marketing at INDO-MIM Limited, based in Pennsylvania, USA. With 12 years of experience in powder metallurgy and 27 years in metal injection molding, Jag has been working on the BinderJet 3D printing process since 2019. Welcome, gentlemen. Over to you, Harish.
Thank you, Sharon. Thank you all for those who attend the session. Really appreciate your time and effort. It's going to be one good session for who wants to know more about tooling from INDO-MIM and talk about real world experiences. I know you came here today to talk about to know more about molding tooling and its benefits and how binder jetting is enabling that. But let me take a step back, and for those who are not familiar with what is binder jetting, what is HP doing here? Let me take a few minutes to go through this process, then I will hand it over to Jack, where the real stuff comes in. So let's start today by discussing why HP is uniquely positioned in this ever-changing, dynamic 3D printing industry. Today, HP offers a top choice industrial manufacturing solutions, especially in additive, both for plastics and metals, with several key advantages to customers ranging from research, small and large manufacturers. Our proprietary HP printheads and latex binder technologies gives us a significant edge that provides the key advantages to customers. In addition to our proprietary technology, we are backed by strong manufacturing core and finance resilience, which is very important today in the additive manufacturing industries. Don't take our words for this, but if you look at it, how many production milestones we have achieved with our partners, our customers out in the field, we have produced over 150 million parts. Our partners have produced 150 million parts using our HP's technology, which is setting a benchmark for industrial applications and scalability and stuff. We are not happy with that. We want to continue drive our innovation, and so that more and more people uses additive manufacturing and sees it as more than a prototyping technology. With that, we launched a MetalJet solution, which is a specific for printing metal parts at scale and expanding materials both on our polymers and metal front, and advancing the software and data services to support our customers. Finally, all this is possible because of our customer-centric approach, where we listen to customers, where we deliver high levels of personalization depending on the requirements, and finally on rapid response times, which are very, very essential in today's dynamic market, especially for metal binder jetting, as you can see. So here we have our HP Metal Jet solution, which is a versatile, scalable metal 3D printing platform designed for research, small and large manufacturers use. Use the same system to develop a material, to develop the application, and you can scale it for making 1,000 parts, 10,000 parts, 20,000 parts, depending on your designs. It includes a modular components for powder management system where you load the powder before going into printing, and you do printing, curing, and powder removal. Each of this equipment is optimized for efficiency and high quality production. This modularity does not only streamlines workflows, but also enables scalability, making it ideal for research, small and large production environments. What does that mean is you don't need to have 10 SKUs to address 10 different customers. You may need to have only one SKU where it meets all the customers. And as you advances in the technology, advances in the application in development, you can use the same platform. This chart here, which shows that demonstrates binder jetting and as well as HP S100 what approach to overcoming challenges in mass production. Binder jetting, as seen with our HP Metal Jet S100, offers a unique balance of production quality and process economics. HP's Metal Jet S100 delivers superior production quality and economics, overcoming traditional limitations in additive manufacturing for mass production. This is all possible because we take it very serious, and it's very significant within inside HP, where we want to combine reliability and repeatability and process economics to deliver high quality parts to our customers and install base. Here you can see the workflow, end-to-end workflow, how our Metal Jet S100 solution works, right from starting from fresh metal powder to finished parts. I'll take a minute to explain each step for those who are not familiar with this process. So to your left, the first equipment you see is a powder management station. And what do you do in your product management station is, when you look at the screen, you find a HP Metal Jet build unit. If you're a big fan of Star Wars, assume it as an R2-D2 robot, which moves from one station to other station or one equipment to other equipment. So this build unit has 3 boxes. The farther end of the boxes is where you put your loose powder or metal powder, which is spherical in shape, sub 22 microns powder, which you would use for building the parts. And the center box is where you do the printing. So you insert this in a build unit in a powder management station. And this powder management station, which has an integrated sieve, comes and automatically loads the powder in this farther boxes in this build unit. Once it's done, you take it out, insert it in the printer. In the printer, this farther end build boxes where it contains powder raises layer by layer, and each layer thickness varies from 30 microns all the way to 70 microns, or it can go up to 90 microns as well, depending on your needs. And a roller comes in, spreads the thin layer of powder. On top of it, a printhead comes in and deposits the binder in selected location. Imagine it is like printing on a piece of paper at your home. Instead of printing on a piece of paper, you're printing on a powder bed, which is metal powder bed. And you continue this process layer upon layer until you get a final 3-dimensional part. What you did here is basically gluing metal powders together in the form of a 3-dimensional shape. But now you need this metal powder binder to solidify, to give a strong part, which we call it as a green part. So you take it off the printer, put it in the cure station where you apply thermal energy for this glue to solidify. Once it's solidified, you have a strong green parts, which you can use for taking out of the powder bed. And all the unused powder, which is not used for printing, is reclaimed and used for next steps of printing. And this green part, which is cleaned in this depowdering station, which is automated, where it does 80 to 90% of job of separating a green part and the loose powder. Once you have this green part cleaned out of this powder bed, you take it to a sintering furnace, which is a third-party furnaces, where HP has designed system in which it produces a part that can work with any type of furnace that's out there which is used for metal printing. You sinter it to close to melting point of material, and once you cool down, you have a solid metal part that can be used for further steps of processing or can be directly used for application. What it tells is this workflow ensures efficient, sustainable production, covering various types of equipment for seamless operations. Each step is designed to maximize productivity and minimize waste for an end customer. Either it can be research, either it can be small manufacturer, or it can be large manufacturer like INDO-MIM. Our machine, our equipment is mostly open material system, where we offer support a diverse range of materials, and it is categorized into 3 steps. When you talk about farther right, is a HP certified materials. What that mean is HP has went through several rounds of testing, qualifying from one powder lot to powder lot, from printer to printer. The center section where you see customer or supplier qualified, in this case, INDO-MIM has qualified their M2 and 360 on our platform in the last 8 to 10 months, where they go through certain printing protocol specified by HP, where they demonstrate high quality standards. And the farther left column where you can see is all the materials HP has evaluated, but waiting for the right customer demand and right customer pull to move to the from left to right. This finally, what makes us different? This is a numbers where we talk about operational efficiency, which is taken from install base. This is not from HP. This is taken from our complete install base. Operational efficiency is a priority for HP metal jet installation. Here you can see the key performance metrics, where you can see 85% overall equipment efficiency on our printers, where we are printing on an average 8.5 jobs per printer, not across all the printers, per printer, with a yield of 92%. These metrics highlights what we want to do in the field, that is productivity, quality, and reliability to our customers, so that we can put real application parts in production. Finally, I would like to take this as a chance to highlight our successful partnership with INDO-MIM. With 3 HP S100 solutions have been placed, 2 in India, 1 in San Antonio, Texas, last year. INDO-MIM has been supporting multiple OEMs and qualified M2 and 316L powders for our platform, and with more to follow. Finally, this partnership demonstrates how HP Technologies enables large-scale production partners like INDO-MIM, where we can support diverse manufacturing needs across different regions, and also continued our collaboration for bringing out new materials and bringing out new solutions to the customers that haven't experienced additive manufacturing before. With that, I would like to introduce to Jag Hola from INDO-MIM, who is our continued champion and great partner. Jag.
Jag, I believe you're still on mute. There you go.
Yeah. Okay. Yeah. Good morning. Good evening. Considering where you are calling from or attending the webinar, it's our pleasure today to share some of our experiences with the binder jet 3D printing as applied to producing tool elements. But before we dwell into more details, let me introduce INDO-MIM. I'm not able to move the let me introduce INDO-MIM before we get involved, get into more details about the tool elements and how we adopted binder jet technology. for producing the tool elements. INDO-MIM primarily is a metal injection molding company. We are one of the largest in the world, and we have been in the MIM field for over 25 years. We ship to more than 5 continents. We ship approximately 150 million parts per year. We have a production floor space of around 125,000 meters square. We service around 650 customers globally, and we service more than 8,000 MIM programs on an annual basis. And we also are involved. We got involved with the binder jet 3D printing since 2019, ever since the binder jet process started coming on the horizon. So we have probably accumulated, one of the best experiences in the binder jet technology, working with the partners like HP for more than 4 to 5 years. But what sets us apart also, is we also manufacture metal powder for additive manufacturing. Originally, we started making these powders for our own captive requirement for the MIM process, but then we expanded our capabilities into 3 gas atomizers, where we currently produce powders for binder jet, LPBF, thermal spray, cold spray, pretty much, where metal powders are required, anywhere between 3 microns to 140 microns particle size distribution. We are in a position to, make those powders. Now, let me also explain, why we got interested in producing the tool elements through the 3D printing. Considering that, we are a very large MIM company and service close to 10 to 12,000 programs, MIM programs globally, and also launch around 300 new MIM programs every year. You can imagine, the amount of tooling requirement that is required for running our business. We have a very, very large tool room that is capable of producing close to around 900 molds, MIM molds per year. And traditionally, we have been doing production of the mold through conventional machining, which is a very, very acceptable process that most of the tool rooms in the world follow, basically machining it from the bar stock. But this process, I think definitely, we all understand that has got a lot of drawbacks. As we are exposed to more and more newer technologies, we start seeing, the drawbacks with the conventional method of working. The conventional production of the tooling involves, several machining steps. It involves, a large number of experienced tool makers that are very hard to find these days. And then, of course, the conventional metal machining, for producing the tool elements does not give you a lot of design flexibility that 3D printing can give. And about around 10 to 12 years back, many of the tool rooms, including INDO-MIM, we started adopting the 3D printing process. But those days, before a couple of years back, we only had the option of printing the tool elements using the LPBF process. It was a great switchover from conventional machining to a 3D printing. We were able to, significantly improve our productivity. But the problem with the LPBF was it still was a very slow process considering the binder jet, and scaling up was a major issue. And also there was not many materials available through the LPBF route. Most of us actually used only the maraging steel with only 55 HRC hardness, which was not good enough for a lot of tooling applications. So that is when, we diverted our attention to 3D print these tool elements using the binder jet process. Now the question is, why binder jet? Because LPBF and binder jet both are 3D printing processes, but the advantage with binder jet, is it is approximately 5 times faster compared to the laser bed. In a laser bed, you can probably print a build box in 3 days, whereas we can actually print a full build box in less than 10 hours or 12 hours. And then the binder jet also offered us, a large variety of material options. Right now, we are extensively using the M2 tool steel for producing 3D printing of the tool elements. But in the less than 12 months, I think, we will be able to cover a lot more tool material that are popularly used in the tooling industry. So scaling up is not a problem because of the speed of the process. And you don't anymore need, a lot of experienced tool makers. And the workflow is highly scalable. That was one of the reasons, why we really started putting a lot of energy into producing the tool elements for tool for the binder jet for the tool elements. Now let me quickly touch base on the benefits of binder jetting for tooling, which is very similar to all the advantages that industry has been enjoying for the last decade through the laser bed fusion. So that's why I don't want to spend too much time, but we all know that the binder jetting or a 3D printing process allows us to use a conformal cooling technology, wherein you are now able to take the cooling channels very, very close to the molding surface, which means that you are able to cool the part or heat the mold elements during the molding process more efficiently. So that actually solved a lot of other issues that we will, as we move along, I will bring you up to speed on the kind of advantage that we experienced because of the conformal cooling. We were able to solve a lot of sink issues. We were able to solve a lot of distortion issues. That more of those details we can get to. So these are some of the examples of the mold elements, just for your reference. We printed actually the mold elements that are as small as 300 grams, but we also printed mold elements that are as heavy as 10 to 12 kilos. As you see here, some of these cavity, the mold cavity that you see on the picture here, they are easily around 8 to 10 kilos, which is quite surprising, for a 3D printing industry, where normally, the LPBF, especially in the mid-level situation, you don't really print more than 4 or 5 kilos of material. Now, coming to the real world example, I want to bring you up to speed on, these are actually examples taken from our operation, our tool room. Now, how do we know that, a 3D printing, binder jet 3D printing, we are able to achieve the required success compared to the conventional method of manufacturing? So what we did was, we focused on a few key elements. One of the key element was, as we all know, in an injection molding process, it's important that, we have a uniform temperature on various elements of the mold so that you can mold efficiently and cool the part efficiently. So we focused on the temperature study of the various sections of the tooling on the 3D printed mold elements and see, if there is any advantage. And once we looked at that, we also compared that, okay, what kind of quality improvements, we were able to achieve on the component by using the binder jet 3D printed mold elements. And obviously, we were also looking for cooling time reductions. Are we able to reduce the cycle time, from 40 seconds to 30 seconds or 30 seconds to 25 seconds on a production basis, because now you are able to heat the mold and cool the mold more quickly than we were doing earlier. And most importantly, we also focused on, is there a real, improvement in the mold life? Because when we switched over from wrought M2 to miraging steel laser bed fusion, we were very disappointed because, the mold life actually dropped because we were not able to get the required hardness on the laser bed printed tool elements. Because we are now able to do M2 material with 63, 66 HRC hardness, so we are hopeful that we will be able to get a very, very a big improvement in the tool life. So we focused on that as well. So I'm about to present some of those findings for your reference here. Now, starting with the conformal cooling, how it really helped us to maintain the uniform temperature across the mold element, which helps both in cooling the component uniformly and at the same time, also mold the component so that the material does not freeze unduly at certain areas, because you are able to maintain uniform temperature across the mold elements. Now, if you look at the tool element, the picture here, the conventional cooling, the conventional tool design allowed us only a straight line. That means, the cooling was very, very inefficient. Because we adopted the 3D printing, the conformal cooling tool design allowed us to take the cooling channel as close as possible to the molding surface. Now, if you see, the initial temperature was, of course, before we started molding, obviously all of the mold elements were exactly at the similar temperature. But when we run 15, 20, 30 cycles, what happens, is for the lack of appropriate cooling, certain elements on the tool element become significantly hotter than the other elements. And that actually caused a lot of quality issues, in the process. By adopting the conformal cooling tool design, if you see here on your right side, the temperature difference between the various tool element dropped to only 0.5 degrees Celsius compared to 6.3 degrees Celsius, on a conventional mold. And that was a huge advantage for us, and we were not able to achieve that with the conventional tool design and conventional tool manufacturing. Here is another example, where we were able to drop the temperature difference to only 4.8 degrees C compared to 14.1 degrees C, in a conventional method. So these things, really went a long way in terms of helping us to improve the molding quality and the quality of the product. Same thing here, if you look at this component, we struggled a lot with the conventional method of producing the tool because we were not able to cool the mold or heat the mold, adequately or uniformly. We always were struggling with a void in the middle of the component. As you see here on the X-ray, there used to be a void which we could never get rid of, and that was not really good for the strength of the component. So when we switched over to a conformal cool design, to our surprise, that void actually vanished completely, and we were able to produce quality product without having to worry about the integrity of the component. So the same thing was, with relation to the elimination of the sink defect. So what happens, as we all know, if the component, has got a lot of hot spots, when you are molding, that actually results in a sink, and then eventually a void created because of the sink. And those kind of defects, we were able to completely eliminate. If you see here, the conventional slide, you were only able to drill straight holes, but on a conformal cooled slide that was 3D printed using the binder jet process, we were able to take the cooling channel all the way to the surface of the molding. Now, the kind of sink that we used to see all the time, by changing the mold design and method of mold manufacturing, we were able to completely eliminate the sink on the component. And the same thing here, if you look at this component, because of the uneven cooling, if you see the conventional tool design, you only see the straight lines. So that actually was not sufficient for a uniform cooling on the slot area here. On a 3D printed, the tool design, you were able to get a conformal cooling channel, much closer to the air where the cooling is required. So we were able to significantly reduce the distortion in the slot, considering that, we were doing 100% inspection, sorting out and lose 10-20% of the component. We were able to get 100% yield, and we eliminated even inspection as well, because we were so confident about the process with the new design. A similar is the study case here. As you see here, the slot at the back end was always an issue, and we were able to resolve that issue, by 3D printed conformal cooled inserts. Now, that was all about the cooling, but we also noticed that, this conformal cooling can also be reversed into a conformal heating. If you look at this component, this is a very small component with a very, very thin wall. And we always struggle to fill the material, because the metal injection molding is not like plastic. We are trying to injection mold a semi-solid material. So as the wall thickness reduces, the material loses its heat, very, very rapidly. So it's important that, until the last fill point, the mold remains at a particular temperature, and that is only possible if you are able to heat the mold uniformly during the part of the filling cycle. So in the conventional design, we only had a straight line, and we really struggled with filling this component. But then when we redesigned the part with a conformal, I'd like to say heating, so we were able to pass the heating liquid into the cavity and keep the mold, at a required uniform temperature, so that we were able to fill very effortlessly. And because of that, the crack and other issues that we used to see in the component completely vanished, when we actually use the conformal cooled inserts. Now, coming to the cycle time reduction, because we were able to quickly cool the components after the molding is over, we always anticipated that, the cycle time would probably will reduce somewhat. But we were surprised that, we were able to pretty much achieve anywhere between 10% to 40% lower cycle time on the molding cycles, across the board. The minimum we were able to see around 10%, but some places we have seen 40 to 50% cycle time reduction. Now, when you are running programs, that are hundreds of thousands of parts per week or per month, every second that you save on the cycle time goes long way in terms of the cost reduction. So you don't have to add more molding machines. So your overall, the cycle time, overall productivity of the shop floor will significantly improve. And for us, the biggest surprise also was the mold life improvement. We thought, there could be probably 20-30% improvement in the mold life. And that was a huge requirement for us, because when you are running 1,200 molds in a year, and then you produce 900 molds and when you support 12,000 programs, there is always a requirement of replacement molds. If the molds are wearing often, that will actually put a lot of burden on the tool room, and then you just keep investing on the tool room, which is not productive at all. So we were able to see, in fact, on one of the component, as you see here, we were able to see 600% improvement in the mold life. The way we calculated the mold life also was, between starting off using the mold to the time, where it starts flashing first, how many cycles, the mold is able to run. Because each flash correction is a burden on the tool. The tool is pulled out and it goes to the tool room. You spend a lot of resources. To that time, to that extent, you don't have the mold in the production. So it is really a pain point for us. So we were able to see on the first tool that actually completed its life now, we were able to achieve almost 600% improvement in the mold life. There are a lot of other molds, that are currently running in production. Pretty much, all of them are still running, and we are seeing already, anywhere between 15% to 215%. And these molds are actually still running. So by the time they are done, we are hopeful that, on an average, we will be able to see anywhere between 200 to 300% improvement in the mold life, which is a huge deal. If you are actually a tool dependent, if you are running a tool dependent technology for day-to-day business. So coming to the, how are we able to achieve these things? Of course, the people have always used the wrought material, wrought M2 for producing the tool. What they are not able to achieve, how binder jet material is able to achieve, So initially we were also a little surprised, but then when you really metallurgically analyze and go back and compare the microstructure and all that, it is very clear, why a 3D printed binder jet tool element, behaves that way and is able to offer you 200 to 300% improvement in the mold life. Now, we really didn't do much of a change on the chemistry part of it. As you see here, the chemistry pretty much comparable with the wrought material. And similarly, the material properties, the yield strength, UTS, hardness, density, etc., they're all very much in line with the wrought material. But the big and then of course, we, in addition to the tool life study and all that, we also did some fundamental R&D work, in trying to one-to-one compare the machinability of the 3D printed M2 material. What we did was, for the lack of any kind of an organized method to understand the machinability, the difference between the machinability of the wrought and the binder jet material, we just took, a big block and we started drilling a 4 millimeter hole until, the drill bit no longer produces a good quality hole. To our surprise, a wrought material produced only 28 holes at the 64 HRC hardness, whereas a binder jet material, we were able to take it all the way up to 46 holes, without damaging or without, getting into a poor quality of the hole. Same way, we also conducted the lab level, we conducted the wear resistance. How come we are able to see, 200% minimum, improvement in the mold life? So there has to be something to do with the material wear resistance. So what we did was, we conducted a lab level wear resistance. And as you see here, the 3D printed LPBF version, that is a maraging steel, there is no surprise there, was the one that actually wore much, much more. You know, a wrought material is definitely 1/3, half of that. Whereas binder jet, by actually further improved, you know, like you are now able to see there is almost a 50% improvement in the wear resistance compared to even the wrought material, leave alone, you know, compared to the laser bed fusion material. So how is all these things possible? You know, okay, we talked about the material, the chemistry, everything is fine, but that still does not add up, right? Now, you look at the microstructure here, because we start with a very, very fine metal powder, and then we also achieve 99.5% minimum density. The microstructure that we are able to achieve on a 3D printed, binder jet 3D printed material is significantly superior. You know, you get, you know, very, very fine microstructure compared to a wrought material. And we all know, you know, finer the microstructure, you know, better is the wear resistance, better is the machinability, better is the wear resistance, better is the life of the material that you produce with it. So finally, you know, we sort of got, you know, a full round answer, you know, why M2 material produced through the binder jet process not only gives you the 360-degree freedom on your design and allows you to do a conformal cooling, which was never heard of, you know, in a conventional tool room, but the material, the process, all of them come together, including the productivity, you know, which is probably around 5 times faster than the conventional 3D printing using the laser bed fusion. So I think, you know, like we have really hit a sweet spot with a combination of all of these technologies coming together, you know. So with that, you know, like I will end my discussion today, you know, our experiences with the binder jet 3D printing and the properties of the material. Now we are open for questions if you have. Thank you very much.
Yes, we do have several questions here. So let's go ahead and jump right in. Don't forget, if you have a question, go ahead, type it in the question box and submit this, click the submit button. So our first question is, how do you manage warpage of the mold insert during the sintering? Are there any preliminary simulation steps?
We do, of course, use some simulation steps, and there is also actually a software, you know, with that HP actually supports with as well, to understand the sintering distortion, you know, ahead of, before even you start sintering. And to that extent, you know, we try to add the compensation. See, the beauty of 3D printing is it's not tool dependent technology. So you can always add material where you think it is distorting in the reverse direction, so that the distortion actually bring it back to the required shape. Having said that, the tool elements itself, you know, are pretty robust in the design. You know, they have decent wall thickness, there are no overhanging walls and things like that. So the application itself, you know, is not really prone for a lot of sintering distortion. But to answer that question, yes, you know, we do use simulation, and then HP has a product that comes with the printer. And then we have also, of course, use, you know, our sintering knowledge and 15 years worth, 20 years worth of knowledge that we have in sintering the M2 material.
I would like to add just one point, Sharon, to that thing. What we have seen with the INDO-MIM M2 powder, we haven't seen a significant warpage in the tools. They're almost as flat as possible. So it can be a combination of technology and the powder as well, how it's working. Again, Jack, correct me if I'm wrong. Yeah.
Yes. Yeah. Right.
Okay, we have another one here. So what is the final hardness of the mold insert? And is there any particular secondary heat treatment or particular heat treatment?
No, we do. We definitely have to do the heat treatment, because the as sintered hardness is somewhere in the range of 50 to 58 HRC. But as sintered hardness, you know, the range is too wide actually, depending on the cross section, depending on where you put the part in the sintering furnace. So we don't want that kind of a variability that is coming out of the as sintered material. So we do have to, we should do the vacuum hardening, just like how we do the vacuum heat treatment of the wrought M2. So the hardness range that we normally target is 63 to 66 HRC. average is around 64.8 or so. However, some applications may not need that kind of a hardness. So we have the ability to temper it down. After the heat treatment, we can also temper it down to 55 to 58 HRC as well. But the hardness is definitely a secondary step required to ensure that the microstructure is more refined and the hardness is in as small range as possible.
Okay, so here's another one. Is there a difference in the polishability of the material compared to wrought tool steel?
No, in fact, that was originally one of our apprehension, because the binder jet M2 gets to 99.5 or 99.6% density, whereas the wrought material is 100% density. So that 0.4 or 0.5% porosity density difference, will that create any kind of a surface porosity or pitting or anything like that? But we were not able to see any such issue, and we were able to polish exactly the same way with the same process to the same level.
Okay. Here's another one. Can 3D printed inserts be used for aluminum die casting tools?
Yes. Yeah, we will be able to use in the aluminum die casting tool, because although your die casting temperature is high, roughly in 600 or 700 degree C, the tool elements, because of the cooling channels inside, they actually stay typically below 300 degree C. And that actually is okay for the M2 material, because the M2 material starts losing its hardness, beyond 450 degrees C. So there are examples, and as we speak now, there are at least half a dozen locations, our customer locations right now, where our inserts are currently working, without any issue.
Okay, so how long did it take for HP and INDO-MIM to collaboratively develop a new material and scale production for these parts?
M2, it probably, correct me if I'm wrong, Harish, it took probably around 6 to 7 months since we decided to adopt M2 on the HP platform.
That's correct. Since it's our first material for collaboration, it took us little more time for us to fine tune to INDO-MIM process, INDO-MIM fine tune their material and sintering to our printing technology. But the new material, 316L stainless steel, which will be announced at Form Next, it took us almost like 45 days, 45 to 60 days.
Yeah.
So as we go on, I think since we know how our INDO-MIM knows how our printer works, we know how INDO-MIM sinters and how their powders are, I think this becomes more faster. So depending on the customer requirements, I think INDO-MIM and HP are looking forward to develop more and more such materials in the future.
I mean, it is precisely a two-step process. The first step is to adopt the powder for printability, the binder compatibility and things like that. But once you print, the second step, is sintering the material to the required density and the microstructure. So it's basically a two-step process. Sometimes, if depending on how difficult the material is to sinter, it may take a little longer time. It could be anywhere between, I would say, 4 weeks to 4 months, I would say, depending on how the material behaves during sintering.
Okay. All right. So have you had experiences with cold extrusion die applications?
We don't have a lot of experience. However, we do have actually 2 experimental tools that is actually going into a production run for testing in the next 2 weeks' time. So the one thing that INDO-MIM offers, is for any application, it could be injection molding, die casting, cold extrusion, hot forging. It could be any tooling application. As long as we feel confident, we offer one tool at no cost to our customers for them to actually test the technology, so that we can sort of establish a technology together for their application, so that like it could be a running production program for us as well. And of course, not to talk about the cost reduction that customer is going to enjoy.
Okay. Here's another one. David asks, when you mention molding information, is that MIM or polymer IM?
It's MIM because we are a MIM company. So everything that I presented over here, they're all related to MIM. So, but I would imagine that, for the polymer molding, this can be even better actually, because normally, the MIM molds do not last as long as the polymer injection molds. But if these tools can withstand the MIM level of stress and the wear, I'm sure, if you adopt the M2 tools, your 3D printed tools for the polymer molding, the results would be fantastic. And again,
Okay,
like we are
oh.
more than willing to, offer a free tool if someone wants to try, at their shop. Sorry.
Okay. He also wants to know what mold tolerances have you been able to achieve with BJT?
The mold tolerances as sintered, of course, are not very accurate because the sintering process with the 3D printing process itself is almost in the range of a total of around plus minus 1% of the feature size. However, we will not worry so much about the tolerances coming out of the inserts out of the furnace, because these tools, these have to be finished, to fit in your mold anyway. Pretty much, that finishing part of it we cannot avoid. However, you have actually a tool that is almost 95% already finished as printed. So your finishing time and the resources required for finishing is significantly drops actually.
Okay, what is the typical material and mold injection temperature?
For the MIM, its injection temperature is roughly around 140 degrees C. And currently, like traditionally, we have been using M2 tool steel, wrought M2 tool steel, and that is what actually prompted us to look at binder jet M2. And I know many of the polymer molding, tool rooms, the people who produce the molds for polymer molding, they use actually H13 and they use A2, P4. There are a few other tool elements. So our intention also, is we believe that they can very easily switch over to binder jet M2 material without losing anything, but only with a significant advantage that M2 brings to the table. However, if you don't want to change, 2025 INDO-MIM and HP, we are also bringing more popular tool material with the tool chemistries to the binder jet platform.
Okay, Thomas wants to know if this M2 material was already released by HP and open to all users.
Harish, can you pick that up?
Yes. So it is open because INDO-MIM has qualified it as per the HP protocol, and all the data you've seen on the mechanical properties, microstructures and stuff was collected following HP's protocol. So if a customer wants to buy M2 material, they can directly reach out to INDO-MIM, and INDO-MIM can share the specs that's developed for HP's S100 solution and support their needs. And HP, as usual, will support their with their printing needs and other accessory supports.
All right. Clemens wants to know what kind of plastic material was transformed in those molds. Any flame retardant and glass fiber load?
No, see the MIM process, the way the MIM process works is it is 95% metal powder. It could be steel, stainless steel, copper, not aluminum, but it could be steel, stainless steel, nickel superalloys, and all that. The 5% is actually a polymer binder. It's not a single component system. It's a multi-component system. The way the process works, is you take metal powder of the required chemistry. The particle size distribution is normally anywhere between 3 microns to 25 microns with the appropriate distribution. You mix that with the polymer under heat. That means the polymer actually melts during the mixing process and it actually coats the metal powder. And then you palletize them just like the plastic granules so that you can store them, transport them. And then when you take it to the molding machine, injection molding machine, you plasticize the material just like how you do in the screw. The material gets plasticized, except that in the polymer molding, the entire material becomes liquid. Whereas here, it's only the polymer, that 5% plastic that we added, the binder that we added actually melts. So you actually convert the whole thing into a semi-solid paste. And that material actually is injected into the cavity. And there is no fear of anything catching fire or anything like that. And we don't use any flame retardants or anything like that.
Okay, I have another one here. What is the cost reduction of the mold insert manufacturing compared to standard manufacturing or LPBF? Does it require additional machining operation after sintering, heat treatment?
LPBF, comparative to LPBF to binder jet is definitely cheaper for one reason. The reason is the binder jet process itself is 5 times faster printing wise. So you are able to print the part much faster for almost same cost of the printer. And sintering really does not add a lot to the cost, because sintering is a bulk process. You have a very large furnace. You can load like 300 kilos of material into the sintering furnace. In the end, it will only works out to like $10 to $15 a kilo, depending on the material. So sintering really does not add to the cost. So to answer that question, the binder jet 3D printed tool insert comparatively is much cheaper compared to a LPBF 3D printed insert. And then, of course, binder jet offers you, much more material options. Binder jet offers you M2 grade material, whereas the LPBF, you cannot do LPBF 3D printing on any material that contains more than 0.5 or 0.6% carbon, which is a huge bottleneck because a lot of tool materials are a high carbon material.
Okay, so are there any issues with nickel plating this material?
No, not at all. None. We have done nickel plating, we have done cermet coating, we have done the PVD coating. It behaves exactly like a wrought material.
All right. And then Francisco wants to know, for how many printing cycles can the powders be used? And is there any kind of contamination or assessment test to predict it?
To answer that question, is we don't really straight away use the powder. It goes through some processing, and then we mix the virgin with the used powder in a certain percentage. And because of that, the powder material can be endlessly used, because you are actually regenerating the powder for the next build box through, the sieving and, mixing process. So, eventually you really don't lose a lot of powder. On an average, our experience is that you don't lose more than 5% overall on a long-term basis, the powder. Pretty much 95% of the powder gets used again and again and made into parts.
Okay, I have another question here. What is the ability of these inserts to be modified after sintering, for example, for dimensional or design purposes?
Oh, you can machine it. Once it is sintered, it's a solid steel, right? It's 99.6% density. You can grind, you can mill, you can do whatever you do on a normal wrought material. You can do it and you can modify it once it is sintered.
Okay, and I think we have time for one more question. Let's see. Can HP's metal jet technology confidently manufacture thick tooling parts at scale while maintaining quality and consistency?
The answer to that is yes. However, the thick, is a relative term. What we have done, is so far we have not experienced any issue up to 16 millimeter wall thickness. Beyond 16 millimeter, it's not that, we introduce any kind of a quality defect or anything like that. But beyond 16 millimeter wall thickness, there is also a process post printing called a curing. Now, that curing process takes a very, very long time if the wall thickness is too high. And at that point of time, you probably are, wasting the printing time, trying to cure the material, because the same build box has to go back for next printing, right? So you are sort of holding that up, but otherwise, up to 16 millimeter, which is, I think, more than enough for most of the tooling applications, no issue at all in this, as far as the quality goes.
Okay. Well, it looks like we have run out of time today. So if anybody has any other questions that we didn't get to, we will get back to you via email. And that concludes today's presentation. On behalf of Machine Design, I'd like to thank Harish and Jag for the presentation today, HP in partnership with INDO-MIM for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of the day.
Thank you very much.